Hello everyone, welcome to the lecture 52 of the course Diffusion in Solids. We have been talking about the diffusion or rather the key features of diffusion in different classes of materials, and today we are going to talk about the diffusion behavior of one of the very recently developed class of alloys which are known as high entropy alloys. Although some studies here and there were done before, but the major research in this field has been carried out only for the last 20 years or so. So, let us see what are these high entropy alloys and talk about some of the key aspects of diffusion in these high entropy alloys. So, we will be talking about the core effects and the diffusion behavior in these alloys. Now, what are high entropy alloys? See, you know the conventional alloys like steel, for example. You have a major principal element like iron, which is there depending on the steel type, and at least 90% or if not 90 in the majority of chunk. In plain carbon steel, you have only iron and carbon, iron being the most dominant. In certain steels, you have iron little less maybe, but still it is the major component. So, all the conventional alloy design relies on having one principal element and adding small amount of elements to it as alloying additions in order to enhance certain properties. The novel design concept of high entropy alloys are that it combines the elements in equiatomic ratio, equiatomic or near equiatomic ratio. So, this diameter of the circles represent that these are taken in the equal amounts. So, let us say if you mix 5 different elements in equiatomic proportion, now which of them you will call as a solvent, which of them is you call as a solute, or which of them is the principal element here. So, that is the novel concept of the high entropy alloys. So, formal definition if we want to put, it is like, or one of the definition rather, is multi-component alloys with at least 5 elements in 5 to 35 atomic percent. So, it is usually atomic or near equiatomic ratios that are taken. Now, as I said that high entropy, the major research has been carried out in last 20 years, but long back in the 18th century, the French scientist Carl Franz Archard studied multi-component equimass alloys with 7 elements. So, there he studied the equimass alloys. Then later parallelly almost Brian Cantor, J.W.A. and S. Ranganathan brought insights in the field of the multi-component alloys. This was early 2000s, and where Cantor formulated a single phase FCC phase centered structure called a Cantor alloy. This was consisting of cobalt, chromium, iron, manganese and nickel. And Ranganathan proposed the idea of cocktailing effects in 2003, and this is the reminder that properties of HEA cannot be simply calculated by adding the properties of individual components, but it is much more. And then Professor Ye, the JWA, he coined the term the high entropy alloys. And then another is B.S. Murthy, who published the first paper on high entropy alloys by route other than the liquid melting route, which is the mechanical alloy. So, since the advent of high entropy alloys, now people started talking about the alloys in terms of their entropy, or rather the configurational entropy, which is then the alloys are now talked about as low entropy alloys or traditional alloys, then medium entropy alloys and high entropy alloys. So, if the configurational entropy is greater than 1.5 R, then it is called as high entropy alloys. If it is in between 1.5 to 1 R, it is medium entropy alloys, and if it is less than 1 hour, then it is low entropy alloys, or you can call it as conventional alloys also. During the last 20 years of research, so much have been investigated, but people have also started to realize that there is more to entropy in these high entropy alloys. Hence, people have started giving different names also, like complex concentrated alloys, baseless alloy, multi-principal elements alloys, and so on. But nonetheless, irrespective of the name, these alloys offer exciting opportunities to explore a vast compositional space. You go to the center of the phase diagram, because remember, in the conventional alloys, since you are adding elements in a very small amount, the alloying additions are in the small amount, you are primarily sticking to one side of the phase diagram. But now with the equiatomic additions, you go to the center of the phase diagram and uncover more exciting signs. Then you started looking into entropy, because earlier the alloy design is not connected to the configurational entropy. So now that has brought more revisiting the concept of configurational entropy and its effect on the alloy design. So some of the promising features that these high entropy alloys have shown. Of course, there are several good review articles that are available. You can refer to them, but they show very good stability of mechanical properties. For example, here hot hardness is shown as a function of temperature. You can see that the decrease is least for this particular high entropy alloy when you compare with others. Similarly, here also certain alloys come to very high values, the high entropy alloys. Then the wear resistance of some of the high entropy alloys have been very promising, very high wear rate because of the hardness they show. And what is expected is that in the future, we started from the conventional alloys, then high entropy alloys. Now people have also started talking about the high entropy nitrides and the carbides and the oxides. So basically, the design concept of high entropy is coming into several material systems. Now, what is so exciting about this high entropy alloy, or what does this mixing in equiatomic proportion a number of elements bring into, has been postulated as the core effects. So the core effects that arise because of this design. So these core effects are, the first of them is called as high entropy effect. So that means that if you talk about the configurational entropy, it is written as minus R xi ln xi, summation of xi ln xi. The delta G mix we have seen before, that it is equal to delta H mix minus T delta S mix, which contains both the terms thermal entropy as well as the configurational entropy. Now, this configuration entropy, if you let's look at the binary system, then you have a minus R xa ln xa plus xp ln xp, and if you differentiate this dou des delta S configuration by dou xp, then you will see that you end up in an expression where dou delta S configuration by dou xp is equal to minus R ln xb by 1 minus xp. Now, this will be maximum when this derivative is 0. So, for this derivative to be 0, the factor in the log should be equal to 1, which implies that xp is equal to 1 by 2. So, if xp is equal to 1 by 2, then for the binary system x also equal to 1 by 2. So, that means the delta S configuration is maximum at the equiatomic composition. So, this can also be extended to the multi-component system. So, for n component systems, delta S configuration is minus R xi ln xi, and similarly it is maximum when xi is equal to 1 by n. So, if you put this value of 1 by n here, you will see that the delta S configuration max is equal to R ln n. So, this increases as the number of components increase. And as the number of component increases, because the delta S configuration is increasing, it leads to the reduction in the Gibbs free energy for solid solution formation. So, therefore, in spite of having the number of elements, so for example, if you see if 5 elements are there, then if you go back to your Gibbs phase rule, which is P plus F is equal to C plus 1, you will see that the maximum number of phases that can be stable for, let us say, a 5 component system is around 6. So, but what you observe in reality is only simple solid solution structures. So, that is what is exciting about the high entropy alloys, that even having so many different elements, the configurational entropy tends to stabilize the solid solution structures. So, this is one example which is shown here. So, you see that as you have high entropy alloys, 5 elements, 6 elements, still you have only simple solid solution structures formed. So, that even with 7 elements here, you do not get intermetallic or a lot of number of phases, but you get only 2 solid solution phases. The second core effect is the lattice distortion. So, if you have in your lattice only one type of atoms, then it is not a distorted lattice, but imagine if you put in the same lattice different types of atoms which have different sizes, then this lattice will be distorted, and this lattice distortion can cause certain strain to the lattice, which can affect the properties of the alloys at different length scales. Then you have a cocktail effect, which is more I would say it's like a poetic term, which says that when you combine the elements in several atomic percentages or several elements in near equiatomic proportions, then the combined properties is expected to be more than the sum total of the properties of the individual elements. So, this is not really what you can say quantifiable effect, but it is more of a notion that when you combine the elements in different fractions, or then the sum property is more than what you get from just summing the individual properties. So, it is like a cocktail. Then the fourth very important effect is what is known as the sluggish diffusion. So, what is expected is that when you have the different elements, your defects will be surrounded by varied chemical environments, which can lead to enhanced energy barriers for diffusion. For example, if this is a high entropy alloy matrix consisting of several different type of elements, and if you look at these two vacant sites, now this vacant site has a different surrounding than this vacant site. So, therefore, like this your defects which are responsible for the diffusion can experience variation in the chemical local environments, which can lead to enhanced barriers. So, this is one sluggish diffusion effect that people have tried to observe. Now, remember, this core effects in high entropy alloys, although they were postulated, not all of them are completely correct. So, that means there have been several exceptions found to each of the core effect, and experimentally when people started measuring, they realized that there is much more to high entropy alloys than just the number of elements. So, before we go on to some aspects of diffusion measurement, so far the diffusion measurement techniques that are used for HEAs are the tracer diffusion, the SIMS, secondary ion mass spectrometry, and EPMA. These are the primary techniques used for high entropy alloys. In the EPMA, people have tried to make the diffusion couples, where diffusion couples people have or the researchers have tried using a pseudo binary approach. So, design a diffusion couple such that although it is a multi-component alloy, you only get the gradient for 2 of the elements. Then if you do not use the pseudo binary way of doing it, then you make multi-component diffusion couple, and it gives you an opportunity to understand the diffusional interactions as well. So, this is an example. Let me also add here that other than the experimental techniques, people have also attempted to calculate the diffusion in HEAs through computational tools like first principle calculations and molecular dynamics. This is just an example of the grain boundary diffusion measured in HEAs. So, this is in the type C kinetic regime, whereas this is in the type B kinetic regime, where you can see the clear distinction between the bulk and the grain boundary diffusion. Then for measuring the grain boundary diffusion, it is also important that the segregation is absent. So, such alloys have been also studied before the diffusion to ensure that the segregation is absent. This has been done in combination with transmission electron microscopy and atom probe tomography, where you can see here, for example, in this boundary here you see that there is no segregation of atoms present. Similarly, for here as well. So, in TEM you first confirm that in your sample there is a grain boundary present, and then the atom probe tomography tells you the composition along that grain boundary, and to confirm that the segregation is absent. Because you may recollect that when we talked about the grain boundary diffusion, the segregation factor comes into the picture for the alloys, and quite often we assume that segregation factor to be unity. So, the analysis like this confirms that the segregation factors are unity for before you perform the measurement. So, we also when we talked about the grain boundary diffusion measurements, we also talked about the fact that in the B kinetic regime, for example, you can measure only the triple product, which is given by S delta dGB, and whereas in the C kinetic regime you only get the dGB. So, but if you combine these two measurements, that means you perform a certain series of experiments in the B kinetic regime, certain in C kinetic regime, and if you use the factor, so for example, you can multiply the dGB by delta, so to obtain P, or you can divide the P the P by delta to get the dGB, and you can plot them on the same scale to get the activation energy and more information about the P naughts and D naughts. Of course, assuming that the segregation factor is unity, which has been people have been confirming using the advanced microscopy techniques. So, this is one such example where you have for the cobalt chromium iron nickel alloy and for the cobalt chromium iron manganese alloy. Then in high entropy alloys, what has been also attempted is to measure the grain boundary energy. So, the grain boundary energy is related to the diffusion coefficient by this formalism, which is RT by 2 A naught square Na ln D naught GB by D naught V plus 1 by 2 A naught square Na QV minus QGB. So, where A naught is the lattice parameter, Na is the Avogadro's number, QV and QGB are the activation energies of volume and grain boundary diffusion, and D naught V and D naught GB are the pre-exponential factors for volume and the grain boundary diffusion. So, this formalism basically relates the grain boundary energy to the activation parameters of the grain boundary and the bulk diffusion. So, this has been also attempted. So, gamma GB is measured as a function of temperature for alloys like Cantor alloy and COCR FeNI. So, remember here I am showing you examples from one or two literatures, but there are more literature available for the diffusion in these alloys on the lattice diffusion side as well. So please have a search and in Science Direct or in Scoopus, and you can read papers and you may find it interesting to read. Then people have also tried to measure the diffusion in HCP high entropy alloys. So where for example the concept of mean square atomic displacement has come into picture, where for example this is where the titanium diffusion and scandium diffusion was measured. And also what now people are trying to say, that although the notion of the sluggish diffusion was that the atoms face the different local environments and hence the diffusion becomes difficult. But what now, for example, this picture tells you is that the energy barriers for diffusion for certain sites it can increase. So you can have an increased energy barrier, but you can also have a situation where the energy barrier is decreased as compared to the ideal energy landscape. So that depending on the energy barriers, this is also leads to the change in the interatomic distances, and hence the diffusion behavior can be also different. So that's why it is not necessary that always your diffusion is going to be lower. Now the big question as far as the diffusion in high entropy alloys was concerned is, does the diffusion really become sluggish as you increase the number of elements? Now here I have shown you one example where the diffusion coefficient, or rather the triple product is compared at various temperatures, and here it is compared for, let us say, pure nickel, iron 40 nickel alloy, the 4 component medium entropy alloy and the high entropy alloy. Now you see here this comparison, and you will see that there is a certain temperature above or rather below which you have the 5 component alloy, which is the high entropy alloy, having the lowest diffusivity. However, the reduction in the diffusivity as compared to, let us say, a 4 component alloy or even with a pure nickel is not very large, but okay, you can say it is roughly of the order of 2 orders of magnitude. If you compare these 2 alloys, so you can see that the 4 component alloy, this has lower configurational entropy than your 5 component alloy, which is COCr, Fe, Mni, but still the difference in the diffusivities is not very large. In fact, at the higher temperatures, as you go towards higher temperatures, you see that the 5 component alloy actually shows a higher diffusivity than the 4 component alloy. So now this tells that it is not necessary that as you increase the number of elements, your diffusion coefficients are going to go down. So what it tells is, and if you read a little bit more about the review articles on diffusion in high entropy alloys, so far the understanding has been that it is not just the number of elements which is important, it is the type of elements, because remember diffusion has a lot of dependence on the thermodynamic interactions between the elements. In the alloys, when we talk about, then the diffusion is dependent on the bonds that exist and the interactions that are present between the atoms. So that is also playing an important role than just the number of elements. So although initially in the high entropy alloys, when the postulates or the core effects was put forward, and it was thought that increasing the number of elements will lead to decrease in the diffusivities. Yes, it can be true in certain cases. You may find high entropy alloy systems where diffusivities are deaccelerated as compared to the pure components or the lower order components, but it need not be the case. For example, here itself we see that the COCr Fe alloy shows the lowest diffusivity than nickel and iron 40 nickel in this temperature range, but it at the higher temperature range or in the lower temperatures the trend is slightly changed. So, this is because of the interactions that are present, the thermodynamic interactions which are responsible. So, it is not just the number of elements, but it is the type of elements also which play an important role, and hence what so far the studies suggest is that diffusion in high entropy alloys or the sluggish diffusion in high entropy alloys cannot be used as a blanket term. So, you cannot say that if I increase the number of elements from 1 to 6, the diffusivities necessarily will come down. Yes, you may have a change in the diffusivities, but it will depend upon what elements you are adding rather than only the number of elements. So, with this we end our discussion on diffusion in high entropy alloys. We will continue with further systems in the coming videos. Thank you.